Baltimore! RailsConf! Good day. Good morning. So, where do the atoms in your body come from? Stars. Very good. Who said that? Never mind who said that. I can't see a thing out here. But it's okay. Stars are the right answer. The universe began in a burst of energy, probably infinite energy, probably infinite density, although we can't see back that far in time. We can only see back to about 10 to the minus 47th second after that. And there's an awful lot of exponents to go back beyond that, so we're very far from seeing how the universe began. But at least we know that at about 10 to the minus 47th second, there was just this glob, maybe the size of an electron, that was pure energy. Nothing else in it, just energy. But as it grew and expanded, it condensed. The energy started to condense out into real matter. And the real matter that started coming out of it, maybe within a second or so after the Big Bang, were things like protons and neutrons and electrons. Quarks actually came out first, and then they would assemble themselves into protons and neutrons, and the electrons came out about then, and in almost equal parts of matter and antimatter. Almost equal parts, and that's important, because after about, another fraction of a second, all the matter and antimatter reacted with each other, creating loads of gamma ray photons, and there was a tiny bit of residual matter left over, which is us. Now, it wasn't us then, it was hydrogen, and a little bit of helium, and not much else. No carbon, no oxygen, none of the atoms that we're used to, no gold, the gold in my wedding ring, that hadn't formed yet. That happened about 200 million years later, when stars began to form. But these stars were not your normal everyday star. You see, stars run on fusion, and fusion has to be catalyzed. You can't just take a bunch of hydrogen and fuse it. You need trace other elements to help the fusion go. Carbon is particularly important for most fusion reactions. So in fact, these stars that were forming 200 million years after the Big Bang could not fuse. They had to get bigger and bigger and bigger and bigger until the sheer brute force of their gravity finally coerced these hydrogen atoms into feebly fusing, and they would fuse for a few tens of millions of years under horrible pressure, and then they'd blow their guts up all over the sky. And in that last explosion, the forces were so great that protons would be slammed together into things like oxygen and carbon and uranium and gold and silver and iron, and that would get blown across the universe, polluting the otherwise pristine environment that had existed before. All that hydrogen and helium that was existing before got polluted with trace elements that then catalyzed fusion reactions and allowed real stars and real galaxies to form, and planets and people, and that's where the atoms in your body came from. Of course, we're not here to talk about that. Although what we are here to talk about has a similar feel to it, because what I want to talk about today are 25 zeros. How many of you have laptops with you? Okay, now I'm assuming that's everybody. How many of you have more than one laptop with you? Never mind. There's got to be some. This is a geeky conference. How many of you have phones with you? How many of you have some other kind of computer with you? There are 1,500-ish people in this room. I imagine the number of computers in this room is somewhere over 4,000 or 5,000. Yes, yes. When I started my career, one of the first computers I worked on was a PDP-8. Yeah! PDP-8! 4K of 12-bit words. We ruled the universe with that machine. It had a cycle time of 1.5 microseconds. God, it was fast. There was a disk on this machine, 32K. This was a monster machine. It was the size of a refrigerator. It took thousands of watts. You had to plug it into two 30-amp sockets just to keep the thing going. It was a wonderful, wonderful, wonderful machine right around 1960. You could buy this machine for $20,000, which in today's money is $120,000. And we would do miracles with this machine. But now, let's do a little math. And the math is frightening. That machine, that PDP-8, could do 500,000 ads per second. Your laptop can do 2 billion ads per second, maybe more. I reckon that the laptop you hold in your hand right now that is asleep, or perhaps you are tweeting with it, is 6,000 times faster than that PDP-8. 6,000 times faster. And probably your laptop has within it some n gigabytes of RAM, where n is somewhere between 2 and 8. So it has over 1,000,000 times more RAM. And probably your laptop has within it a disk that is some n terabytes, where n is somewhere between 0.5 and 1.5. So your laptop has several thousand times more disk, several 1,000 times more disk. Your laptop probably takes 50 to 80 watts, whereas the PDP-8 took thousands of watts. Your laptop, well, if I took your laptop and started shoving clones of it inside a PDP-8, I bet I could get 1,000 of them in there. I bet I could buy, for the price of one PDP-8, I could probably buy 50 of your laptops. When you start adding up all those zeros, the millions of times more memory, the thousands of times more disk, the thousands of times more cycle per second, we get to a very frightening number. We get to 10 to the 25th. The laptop sitting idly on your lap, of which there are probably 5,000 in this room, is probably 10 to the 25th more powerful than that PDP-8 that we ruled the world with in the late 60s. Now that should scare the holy bejesus out of you. You're holding something that is 10 to the 25th more than we had 40 years ago. To put that into some kind of perspective, 10 to the 25th is the number of microns to the nearest star. 10 to the 25th is the number of electrons in 4 quarters. 10 to the 25th is the mass of the Earth in kilograms. This is a large number. And the really, really, really frightening part of this large number is, what the hell have we done with it? 10 to the 25th. You'd think by now, well, let's go back in time a bit. Let's go back to 1953. I was 1. And there was a language in those days, a language called Fortran. Who's done some Fortran? Look at that. We got Fortran programmers in the room. Now, this language, what a lovely language it was. It had an if statement. And in this if statement, you did not put any kind of Boolean expression. You simply put a numeric expression. And following the if statement were three numbers. The line number to go to if the arithmetic expression was negative, the line number to go to if it was 0, and the line number to go to if it was positive. That's how we made decisions in Fortran in 1953. There were no while statements or while loops, but there was something called a do loop, which incremented an integer and allowed you to repeat until that integer exceeded some limit. The most interesting part of Fortran was probably the format statement. That's where they seemed to put the most thought. The format statement was how you would output things. It looked roughly similar to what we would now call a printf. Back in those days, they didn't know about quotes. We know about quotes now. You put quotes around strings. But in the early days, quotes hadn't been invented. So what they did instead is they put an integer, which was the number of characters, followed by the letter H, and then everything after that H was the string. So if you wanted to say hello, H-E-L-L-O, that's 5 characters, you would say 5H, H-E-L-L-O. That first H there stood for Hollerith, who was the inventor of the punch card. The language honored the inventor of the punch card. And then there was this problem. We needed to be able to control the printer. We needed to be able to tell the printer when to pop up one line, or possibly pop up 2 lines, or pop up to the beginning of a page. So the very first character you would print would be the control character. And it would be a 1, the digit 1 if you wanted to go up a line, the digit 0 if you wanted to go up 2 lines. They had their things backwards for some reason. I don't know why. The character plus if you did not want it to go up any lines at all. And oh, by the way, I just got that wrong, didn't I? It was a space to go up 1 line. It was a 0 to go up 2 lines. And it was the digit 1 to go to the top of the page. Actually, the digit 1 did not go to the top of the page. It went to printer channel 1. Most of the printers in those days had a paper tape reader in them, and you would punch a hole, and this paper tape was in a loop. The number of lines on the paper tape was the number of lines you would print on a page, and you would punch holes in the paper tape in channel 1, channel 2, channel 3, all the way up to channel 8. And that way you could tell the printer, go to channel 1, go to channel 2, go to channel 3, and it would pop up the page to that place. That was the level of intelligence in 1953. And what kind of code were we writing? Well, we were writing assignment statements, if statements, although they were arithmetic in nature, not logical the way we do them now, and loops. What's changed? What do you write now in Ruby? Do you write assignment statements? If statements? No. I bet I could find one. Loops. The interesting thing about where we are now, after 25 orders of magnitude in improvement in hardware, is that our software has improved by nothing like that. Maybe not even by 1 order of magnitude. Possibly not even at all. Because we are still doing sequence, selection, and iteration. I just abstracted the concepts. Assignment statements are sequence. Selection is if statements. Iteration is do loops. And that is still the fundamental stuff that we do. We, programmers here, massively powerful creatures that rule the planet with our ability to write code, write sequence, selection, and iteration, and that's essentially all we do. Oh, we've gotten lots of clever ways to organize the sequence, selection, and iteration. We put it inside objects, or we put it inside blocks or closures, or, oh, there's all these clever places we put it. But it's still just sequence, selection, and iteration. After 25 orders of magnitude improvement in our hardware, our software remains the same. Who remembers a book called Structured Programming, 1972? Little black book. If you haven't read it, you must go and read it. It is the second book you have to read. I'll tell you the first book in a little while. In this book, Edgar Dijkstra makes the point that goto is not just unnecessary but harmful. He says, please, please stop doing this goto stuff. It's hurting your code. It makes your code unprovable. You can't reason about it if it's got gotos in it. Please, please restrict your code to sequence, selection, and iteration. And he canonized those three. He turned them into the three fundamental things that we do. Structured programming is the limitation of code to sequence, selection, and iteration. By the way, this was hugely controversial in the day. People were up in arms. There was no internet at the time, so there couldn't be any flame wars. But there were plenty of wars in the trade journals. Articles were written left and right about how Dijkstra was an idiot and it was absolutely impossible to write code without gotos, and other people would show them, oh, yes, I can, you fool. And it would go back and forth for a long time. Odd how things work out, though. What language do you know of now that has a goto? Yes, yes. There are some, but we don't use them. Interestingly enough, our languages have all but dropped the structure, and we barely noticed it. The thing that was wildly controversial in the 70s and the late 60s has simply become the way we work. That, by the way, just as a simple aside, is what I believe will happen to things like test-driven development. Wildly controversial when it first started, still mildly controversial, but go ahead, fast forward 20 years, I believe that the languages will simply have testing structures. It may even be impossible in those languages to write code without writing your tests first. And we might not even know. It just would have happened that way. The languages would have just kind of moved us in that direction. Same thing happened with objects. You know, what major language nowadays, there is one, but we'll talk about it later, what major language nowadays is not object-based? Wildly controversial in its time, it has simply been absorbed into the Borg of our software community. Now, this is the Rails conference, and I love coming to the Rails conference because this is where things really happen. You guys are on the edge, right? You guys are doing all the cool stuff. You guys are doing this stuff that's really going to pull our industry into the next decade. So this is a fun place for me to be. But instead of looking ahead for the moment, let's look back a little bit. Where did Ruby come from? How old is this language? Who can tell me when Ruby was born?
Before Java.
Yes, before Java. Well, somewhere near the same time. It was February 24th, 1993. When Matz first conceived of the idea of Ruby. He wanted to make a better Perl. Now, Ruby started out looking a lot like Perl, but over the years, the Perlisms have kind of faded into the background, and Ruby has begun to look more like the other languages that gave it birth, SmallTalk and C. We see a lot of C-isms in Ruby, and we see an awful lot of SmallTalk-isms in Ruby, and the Perl stuff, all those funny little variables that we're so proud we've memorized, they're kind of stuffed away into the background now. We don't like to use them. Where did C come from? How old is C? 1969. 1969, C was invented. How old is Perl? 1987, Larry Wall. And what about SmallTalk? When did SmallTalk come? 71. You see, Alan Kay and Ingalls, Dan Ingalls, I think, had a bet. Dan Ingalls said to Alan Kay, you know, a really powerful language based on message passing of the kind done in Simula would probably take months to write. And Kay said, I could write that in one page. And so the bet was struck, and a couple of mornings later, the first version of SmallTalk appeared on Alan Kay's desk. He had written his one-page kernel of SmallTalk. That's how SmallTalk came to be, but SmallTalk was based on a language called Simula. Simula 67. By the way, that number is the year. 1967 is when Simula came out, and Simula was based on Algol 60, which was based on Algol 58, whose author was the same author as Fortran. There's an interesting family tree here that we're going to talk about. There's another set of languages that are also in the mix here that aren't related yet. The Lispy languages. Who knows Lisp? Okay, not enough of you. We'll talk about that later. Lisp was actually invented in 1958. I was 6 years old, and some guy was already fiddling around with Lisp. It was John McCarthy, and he had invented these things called M expressions, which looked an awful lot like function calls, but he translated them into S expressions, which looked a lot like Lisp procedure calls with the parentheses in the wrong place. He had actually based his language on an assembly language called IPL 56, which had a list basis to it. It was an assembly language for lists. Now, before we get too far back in time, let's also talk about some of the other languages that are current right now. C#. When did C# come about? 1999. Well, sort of. Actually, C# is Java, so you could go back that far. But it split from Java in 99. It was a language called Cool. Anders, Hellsberg kind of split it away from Java secretly and silently, and they produced this language Cool, which eventually turned into C#. But it certainly had some tenuous connection to Java, which was invented in 91 by Gosling. It was called Oak. And he had invented it because he hated C++, and he didn't want to do C++ for this project he was doing to control the hardware inside of a cable TV set-top box. Java, clearly based on hatred of C++, C++ was invented in 79 by Jarne Stroustrup. Jarne invented C++ in 79. He called it C with classes. And he invented it because he got hired by AT&T. And they said, well, you've got to write code in C. And he said, I don't want to write code in C. I'm used to writing in Simula. So he wrote this language that made C look like Simula. So C++ has its roots in Simula, which has its roots in Algol, which has its roots in the Algol 58, which has its roots in Fortran. C, 1969, Dennis Ritchie. How did these guys do this? Yeah, a couple of guys hacking around in the basement. I don't think they had a real project. I think they were between projects, and one guy looked at the other and said, what do you want to do today? I don't know, let's write a language. What should we call it? Well, there's this language B out there. Ours is going to be better. Let's call it C. Yeah, C was based on B, which is a language that Ken Thompson had written also in 1969, which was based on BCPL, which was a language that was written by Martin Richards in 1966, which was based on CPL, which is called the Cambridge Programming Language, which was invented in 1963, which was based on ALGOL 60. You starting to get the flavor of this talk? Closure. The language closure, designed by Rich Hickey in 2008, has its roots in Common Lisp and Clos and Scheme. These are Lispy-like languages, and they don't share a lot of the same family tree as all these other languages. They seem to be on a different thread, although they do come together finally, because Scheme was based on Lisp in 1958, but it was also based on ALGOL 60. The logical scoping, the variable scoping mechanisms in Scheme were drawn out of the ALGOL 60 language. So there is some hybrid mating that went on between these two families in those days. And all of these languages, all of them going far back in time, derived from one another, grown from one another, starting at the same root, all use sequence, selection, iteration. They're just different ways to express that, different ways to manipulate the same fundamental clay that we work with every day. You might notice that I didn't mention Pascal. As much as things change in our domain, and they do change, they change all the time. New languages, new ideas, new patterns, new procedures, new methods. As much as things change, they actually don't change very much at all. They actually stay pretty close to the same. The new languages that we are really getting interested in today, those ideas are recycled from the 50s and the early 60s. Object-oriented design was invented in the mid-60s. Lisp and procedural and functional programming was invented in the 50s and the early 60s. The C basic languages that we use today trace their roots back to the early 60s and the mid-60s. Nothing much has really changed. We might look at our languages like Ruby and think, oh, but it's really just a slightly different twist on something that's been around for a long time. Now, maybe we think, well, yes, but look at the things that have changed. Like, take the internet. What a massively interesting thing this internet is. It spans the globe. It ties us together. Certainly true. But where did the internet come from? Just to prove... Hardware? You said hardware? Yes. Al Gore. No, I've got a little note here that says it wasn't really Al Gore. I think it was Tipper, actually. I think that's the cause. In 1962, this guy by the name of Joe Licklider wrote a paper. And just to prove that irreverence was alive and well in the 60s, the title of this paper was The Intergalactic Computer Network. This is the paper that spawned the internet. Thank God. Somebody with a sense of humor wrote that paper. In 1962, he wrote this lovely paper which described the whole idea. The basic fundamentals of what the internet would be, the protocol, the way the machines would align up. He had it all down, but it took 7 years before the first message was sent. The first internet network was put together in 1969. It had 4 nodes. Those 4 nodes were Stanford, University of Utah, and a few others, UCLA and UCSB. And the first message that was sent was the word login. It was sent from UCLA to Stanford, but only the letters LO got through, and then it crashed. It's come a ways since then. Today, there are 155 times 10 to the 6th websites, maybe. There are 500 times 10 to the 6th people who use it once a week. 500 million people. There are 5 times 10 to the 15th bytes stored somewhere on internet servers. There are probably 75 million servers out there, although that number is probably off by a factor of 5 or 10. The number of electrons in motion to carry the data weigh 2 ounces. And the power that it takes to drive those 2 ounces of electrons around the net is 50 million horsepower, which translates into 1.5 grams of matter to energy per second. The Earth is losing mass at a rate of 1.5 grams per second because of the internet. And what does the internet give us? The web. The worst idea since the green screen, from which it derives. The web, this horrible, messy, nasty structure based on protocols that no sane person would use, based on markup languages that are hideous. How many languages do you have to know to get a goddamn web page up? In 1972, IBM invented the 3270, wonderful machine. Nice big CRT. How many of you remember these things, right? They're called green screens. Nice big CRT. That means cathode ray tube, by the way. They weren't LCDs. Cathode ray tube, nice big screen, green letters blazoned on them. Oh, they were such nice things to look at. And the protocol that was sent to them was a markup language. It was a simple markup language. You could say, oh, put these characters here, boldface those characters, do something else to those characters, make these characters invisible. Oh, here should be a field when somebody types in it, remember the characters. And there was a button you could push on the green screen that would take all of the data entered into the fields and transmit it back. Sound familiar? This is what we've turned it into, based on technology from 1972. It has become the web. HTML and HTTP are certainly different. Not better. Just different. And in some sense, the same. Oh, but we think, yes, but Web 2.0 has come out, and Web 3.0 is going to be here, and HTML5 is going to be here, and life will be great. Bah. Life will be fine, whatever. But all this stuff has been done before. We've done the client-server thing before. All this JavaScript down in the browser is just the old client-server thing, recycled yet again. We're going to go around the loop another time. Around and around we go. And we go around this loop because, in the end, our technology is still sequence, selection, iteration. We go through lots of heat and lots of energy to invent new technologies that are not new technologies. They're just new reflections, new projections of old technologies. Our industry is in some sense caught in a maelstrom, in a whirlpool. It cannot escape from sequence, selection, iteration. All the new stuff we do isn't new at all. It's old, just recycled old stuff. And we claim it's better because we've been riding a wave of 25 orders of magnitude. The real progress has not been in software, it has been in hardware. And we've been riding that wave, claiming the benefits for ourselves. But in fact, there's been virtually no real, solid innovation in the fundamental technology of software. So as much as software technology changes in form, it changes very little in essence. As proof of this, let's look at you guys. You're using Ruby. Ruby is an interpreted language. Now, it almost seems insane that anyone would use an interpreted language. Certainly in the 1960s, nobody would have used an interpreted language. Oh, well, maybe that's not right. There were interpreted languages. There were things like BASIC. And even on a P2P8, we had this nice little interpreted language called Focal that we could write little bits of code in. People have been using interpreted languages forever. But you guys, using Ruby, and I will include myself in that because I happen to love writing in Ruby, we who write Ruby are experiencing a strange juxtaposition. What do you use for an editor? What? Vim. Vim. Which is VI. What? 20 years ago, I couldn't wait to get off of VI. VI? What the hell? Oh, wait, I know why you're using VI. It's because you came from TextMate. There you are, the guys on the front edge, the cutting edge of technology. Ruby, rule the world, and you're using VI. I don't understand. You know, there are people out there that are trying to make IDEs that have interesting abilities. You know, who's used IntelliJ? In Java. Okay, I know I'm not supposed to say that. Java, who's used the power of those refactorings, the power of that tool to manipulate code is enormous. It's unbelievable. And can you imagine that power in Ruby? Can you imagine being able to say, oh, this class needs to be split into two. Command Option C, whoomp, and the class is split in two. This method needs to be moved over to that class. Command Option R, whoomp, and it moves over to that class. This class should be split into a hierarchy. Extract a superclass. Command Option S, whoomp. Why can't we have that? Why can't we have that? Where is that technology? And frankly, I think that the guys who would like to do that are looking at you and going, ah, Jesus, these guys are doing VI. They're not ready for this. Christ, we'll have to wait another 10 years until we wake up. How many of you guys are using WebRat and Cucumber? Lovely tools, wonderful tools. I love them. I love the tools. But I have sat with Ruby programmers as they're doing test-driven development, writing Cucumber scripts with WebRat to access the web system, and they're testing business rules through the UI. What? Testing business rules through the UI? What throwback to the 1970s is that? How can you be testing anything through the UI except the UI itself? Why don't we test through the UI? Because the UI is fragile. Because the UI is volatile. Because the UI changes. Software engineering 101, don't depend on things that are volatile. Don't hang code that's going to have to be changed because of some whim of a web designer. Don't write your tests so that 1,000 of them will break because some guy wants to change the spelling of a menu or the position of a page. I don't mind Cucumber. I think Cucumber's terrific, and I think WebRat's terrific. But when you're testing business rules, you turn off the UI. You don't go through the web server. You don't invoke the controllers. You go right to the guts of it and you say, test that business rule. And then when you're testing the GUI, you don't test any business rules. You cut the whole model off the bottom. You stub it out. You replace it with something that does nothing so that you can test the GUI itself. Languages come in waves. Some of you will remember the waves of the recent past. Right? We've had the C wave. And the C wave came along and it crested, probably around 1979, 1980, 1981, something like that. These language waves look like black-body curves. Right? They start and they rise quickly, and then they slowly decay. And the wave of C probably crested in the early 80s, maybe a little after that. It was followed by the C++ wave, which probably crested right around 1990 and began its decline. The Java wave probably crested around 98, 99, maybe 2000 when the bubble burst. It's in its decline. The Ruby wave probably came along around 2002-ish, cresting. Maybe it hasn't crested yet. It's possible that Ruby is still on the ascendance. I think it probably is, because more and more people are getting excited about it. But don't ever think that it's not going to top the crest and then start its way down. It will. All languages do, because all languages are fundamentally the same. We just go through cycle after cycle after cycle. Something has happened. Something has happened that breaks the path that we've been on, this 25 orders of magnitude. What's been driving this 25 more orders of magnitude? What's the fundamental thing that has driven us through this utterly frenetic increase in hardware power? Moore's Law. And Moore's Law just died. Let that sink in for a minute. It is almost certain at this point that Moore's Law is dead, that our hardware is not going to get twice as fast and twice as small every 18 months, that the headlong rush down those 25 orders of magnitude has stalled. Now, maybe it hasn't stalled completely. Maybe we will still make progress, but I think we can look ahead the next 40 years and anticipate that there will not be another 25 orders of magnitude added to the list. It's going to be different. And already the hardware designers are making changes that are having deep repercussions for people like you and I, because we're not going to be able to ride that curve any longer. We're not going to be able to ride the hardware roller coaster any longer. We're not going to be able to claim the massive benefits in hardware for ourselves, because the people doing the hardware have made some extremely pragmatic and very troubling decisions. In your laptops right now, the chips in there, what percentage of the transistors in those chips are simply to manage the cache? You know, the cache that keeps software writes from going to RAM. RAM, from the chip's point of view, RAM is an expensive resource. RAM takes forever to do anything in. So there's an immense amount of logic to stop anything from going into RAM, to cache it all in little on-chip flip-flops so that you don't have to actually go out on the bus and store something in memory. And the amount of logic taken up by those transistors is 30% of the chip. And the hardware manufacturers are now going, well, we're not going to get any more speed out of these things, but maybe we can get more throughput by taking that 30% of transistors and clearing them out and using them instead for more processors. These processors will be slower. They're not going to be as fast. The machines themselves will be slower, but there will be more of them on the chip. And the hardware developers are looking at us and going, well, now, guys, it's your problem. We can give you more computers, no problem. We can keep the number of cycles per second going up, but not the same way. It's going to be with lots of little computers, slower computers on the same chip. And that has very disturbing implications for us, because our languages for the last 50 years have been written around the idea that there's one machine. And now there's going to be many. Now, we've all had experience with multiple threads and a little bit of multiprocessor stuff, but holy cow, hold on to your hats. Because that's going to change, and it's going to change big time. And that's driving a new look at some very, very old software technologies, particularly functional languages. The whole reason that functional languages are now very, very interesting to people is because of this multi-core problem. And so we see the big people creating functional languages. We see IBM and the Java people doing one, and we see Microsoft doing another because they are trying to hold on to their monopoly of you. Because if they control the language, they control you. But it's not going to work, I don't think. You guys are a good example of how that doesn't work. Ruby is a rebellion language. It's a language to get out from under the umbrella of the big software companies who want to control your brains. And now we see Scala coming out of the Java community and F# coming out of the Microsoft community. And what we see in these languages is big, complicated stuff. Like any big company, they would make some large thing. But there are other languages, other functional languages that are out there that are interesting. There's Haskell, there's Erlang, and my personal favorite is Clojure. And I like Clojure because it's based on Lisp, it's based on Scheme, it's impossibly simple. It's so incredibly simple, it takes very little time to actually learn, and yet it is truly a functional language. It is a very, very strict functional language that has, if you want to do anything non-functional in it, if you want to assign something, if you want to do an assignment statement, you've got to jump through hoops. You can't just assign a variable. You've got to invoke the software transactional memory model. So I have some hope that in that realm, we will start to see some real innovation, maybe for the first time in 50 years. Some real difference to the way we write software. Maybe. We'll see. Who among you has read The Structure and Interpretation of Computer Programs? This is, if you have not read this book, this is the next book you must read. Flush your queue. Doesn't matter what book you had scheduled to read. You must go and read this book next. Because this book is an eye-opener in so many ways. First of all, it's a page-turner. You get this book out, you start reading it, and the pages just fly. Holy cow, that moves at light speed. They're going through topic after topic after topic. They're showing it to you, of course, in Scheme, because it's a book about Scheme. But man, oh man, they're just going through topic after topic after topic. And it reads like a novel. It's exciting. You can't put it down. Wham, wham, wham. And you get to page 216. And you've gone through objects, and you've gone through data structures, and you've gone through algorithms, and you've gone through all this stuff. And then on page 216, they introduce an assignment statement. And you look at that, and you go, what? All this code, all these topics, everything we were studying for the last 215 pages, and there wasn't an assignment statement in there. And you didn't even know it. And then you get to 216, and it's like, wow. Wow. No assignment statements through all of that. And then they introduce a new model of computing saying, okay, now the assignment statement, now that we have to introduce it, it breaks all the rules. It breaks our whole model of computing. We've got to invent this new really complicated model of computing, and they describe it in intimate terms, why it's new and why it's hard. And then you go on another 60, 70 pages dealing with this assignment monstrosity. And then they introduce multiple threads. And once again, they have to reinvent the model of computing. Now that we're doing multiple threads, we have to change the model yet again, and it gets more complicated, more hard to deal with. I love the idea that they equated assignment as a complexity-generating thing equivalent to multiple threads. This is the next book you must read. See the little thing on the screen there? Looks like 4 stars in a cross. That's actually 1 star gravitationally lensed by a galaxy in the foreground, which of course you can't see. Oh, by the way, that was the end of my talk. Are there any questions? Sorry? All right, so the name of the first book I mentioned, which is the second book you should read, is Structured Programming by Dijkstra, Dahl, and Hoare. It was printed in 1972, academic press. You might be able to get a copy on eBay, used books. I don't think it's in print any longer, but it's a classic. In that book, you will find Dijkstra describing structured programming. You will also see Nygaard and Dahl talking about object orientation. They describe Simula 67, and inside there you'll hear all about the rules of object orientation. The second book I mentioned, which is the first book you should read, is a book called The Structure and Interpretation of Computer Programs by Abelson and Sussman. I think it's MIT Press. There are plenty of copies in print. You can get them. Also, their lectures are available for free on the internet. You can download and watch these 2 guys do magic on a blackboard in Scheme. Anybody else? Well, have I heard of Alan Turing? The third book that you should read after the others is a book written by Petzold called the Turing Almanac, I think. Omnibus, the Turing what a lovely story. He takes Turing's entire paper describing his Turing machine is embedded in this book with Petzold going through the history and the reasoning all around it. What a lovely, lovely book that is to read. That's number 3. Anybody else? Clean Code.